making this mistake. So when I look at my 9-1 homework, and it says that I am going to, on the very front, when it says 7 digits are selected to form a telephone number. 7 digits are selected to form a telephone number. And some of you said combination. Think about that for a second. Does the order matter in a telephone number?
Yes.
Does it matter if you dial, 5675 versus 756? Whatever the other number was, right? Order matters. That's a permutation. And then, if I am picking people to play the Beatles, a bunch of you said combination. No. You know what the Beatles are? They're like a singing group, real famous back in like the 60s. I'm not talking about bugs. I'm talking about a singing group. And so, if I pick him to play Ringo and him to play George, that's different than vice versa, right? That is a permutation. I'm picking them for specific roles. No, I'm not answering them. I'm not answering a couple questions.
No, it's about the same question. What do you mean? Picking the 4 actors from like
Yes.
So isn't that is like a combination when you pick it out of the group?
So it's permutation. Permutation is a combination. So I'm both picking from a group. If the order of the choice matters, it's a permutation. It doesn't matter, it's combination. Okay, then the other one I want to look at is that a lot of people I didn't give credit for it because it's not like you don't miss points for it. But I marked it wrong. That very last one, when it says 52C13. I think most everybody got that, 52C13. But what kind of number did you get when you did 52C13? It was large, right? Very, very large. When someone says to you, like my parents live like 3.5 hours away. And when somebody says, how far away do they live? I say 3.5 hours. I don't say, what is that, however many minutes or however many seconds, right? So if you've got this massive number of seconds, doesn't it make sense that you would shrink that down to at least years? Now, a couple people went to centuries, which is fine, but take it to at least years, because no one is going to answer that question in seconds or minutes. Right? That's just too much. Okay? Days, years, centuries. All right. Now, if you have other questions about that homework, please get in here during office hours. I will have office hours tomorrow morning. I need to remember to put that in Schoology. We have no meeting tomorrow that I'm aware of, so I will be in here tomorrow morning in case you care to be here with me. All right. I am ready for a page. It's actually got a number on it. It says 90. And remember, because of time, I am kind of picking and choosing the biggies. So on page 90, I'm going to use problem number 10. All right, so look at the problem number 10. It says use a Venn diagram. So here's my Venn diagram. It says the probability of A is 0.7. This notation means the probability of A. So you can think of it like the probability that someone likes apples is 0.7. The probability that someone likes bananas is 0.4. And the probability that someone likes apples and bananas is 0.2. Now, when I draw my Venn diagram, does it make sense to you that the balls would overlap? Because there are people who you are told like both. Now, do not put 0.7 right here. I know it says the probability like apples is 0.7, but what is the 0.7? The whole circle, right? So since we already know the overlap is 0.2, then what's this section? 0.5. Because the whole apple circle is 0.7. Similarly, what's this? 0.2. Now, this is a probability question. You've got 50% of the people like you just apples, 20% like both, and 20% like just bananas. Well, wait a minute. What does that add up to? 0.9. What does that mean? There's 10% of the people who don't like apples or bananas. Does that make sense to you? Okay. Let's answer the question. Draw a Venn diagram. Okay, we did that. Find the probability that A occurs and B does not. So the next time you see this question, it might not be written out in words. It may use the mathematical symbols. So this says, what's the probability of A and not B? That little prime there means not B. So I like apples, but I do not like bananas. Well, that's easy. What is that? Where are the apple but not banana people? Right here? 0.5. And then B occurs, but A does not. So no A, but B. All right, well, that's these guys, right? 0.2. Find the probability of not A and not B. Well, you already did that. Neither one. No A, don't like apples, don't like bananas. What's that? That's your 0.1. And finally, does the probability of A given B equal the probability of A? All right, well, this we already know. What's that? That's no, probability of A is 0.7. That's 0.7. That was given, the probability of A. Now this, we learned this formula yesterday. Anybody remember? What's this formula here for conditional probability? The probability of A and B over the probability of C. If you guys don't shut up, I'm going to get mad. Okay? Someday I hope you're all teachers and you get to teach the last few weeks of school. You think it's hard being a student? Try being a teacher. It's hard. You're cranky. I know it's hard to believe, but I do. All right, so I got to evaluate this. This is the formula for the probability of A given B. All right, so the question is, does that equal 0.7? So what is the probability of A and B? 0.2. And what is the probability of just B? 0.4. What's 0.2 over 0.4? 0.5. Does 0.5 equal 0.7? Nope. So the question is, are they independent? And the answer is no, they are not. No, they are not. All right, any questions about that? All right, number 11, here we go. If it rains tomorrow, the probability is 0.8 that John will practice. If it doesn't rain tomorrow, there's only a 0.4 chance that John will practice. Suppose that the chance of rain is 6 points, probably. Oh my goodness. How do you think we might approach this problem? Think about what we've done last time. What might be a good one? The tree. Yeah, this is going to be a tree. Now, I'll give you a little hint when you're building a tree. If you're building a tree, more than one thing is happening. In this case, what's happening is we got rain and we have piano. Whatever the question is always the bottom rung of the tree. Okay, the last thing you put in the tree. So the question is, find a probability that John will practice. So down here, I'm going to have practice and no practice, practice and no practice. And then up here, I'm going to have the other thing, which is rain and no rain. So once again, if you've decided to build a tree diagram, the bottom piece of the tree will answer the question. So the question deals with practicing. So that's what's going to go on the bottom. All right, let's start filling in numbers. If it rains tomorrow, the probability that John will practice is 0.8. Well, if it doesn't, if it rains and the probability he practices is 0.8, what's this probability? 0.2. They gotta add up to 1. If it doesn't rain tomorrow, there's a 0.4 chance he'll practice, which means a 0.6 chance he won't. Suppose that the chance of rain is 60%. What is the probability that John will practice? Well, he can practice if it rains, so that'll be rain and practice, 0.6 times 0.8. Or he can practice if it doesn't rain, 0.4 times 0.4. No rain and practice. Or rain and practice. So I can add those up. What is that? Should be able to do that without a calculator. Oh well, it's the last period of the day. Did you get 0.64? So there's a 64% chance that he'll practice. All right, one more. Yesterday, remember we did several probability problems and we did all different kinds. So today so far, we've gone back and done another Venn diagram and another tree. Now number 12 says, Michael makes 90% of his free throws. If he shoots 20, and if his chance of making each one is independent of the other, what is the probability that he makes all 20? Okay, so what that means is, we're assuming that his chance of making a free throw doesn't change no matter what. And what the problem says is, in reality, we know that if a kid steps up to the line and he's already missed 5, his confidence is shaken, so he has a higher chance of missing. They're saying, forget all that, the probability stays the same. All right? So he shoots 20, and you want him to make all 20. So 20 shots, we're going to choose all 20 of them to be makes. So every time he takes a shot, he's either going to make it or he's going to miss it. We want him to make all 20 and miss none. That's what's happening in this problem. There are 20 shots. We're choosing all 20 to be points. What's the probability of making? 0.9. Then the probability of missing is 0.1. So you can type that into your calculator. And he has about a 12% chance of making all 20.
He's on like a row of 20 and 0 on the top.
It says shoot 20 times. 20 of them are makes, none of them are misses.
So is that just like for our own knowledge, or like we don't have to put that in the contract?
Yes, 0.9 to the 20th.
Oh. That's what it says.
These are exponents.
Yeah, that's what I
Yeah.
thought.
All right, exactly 18. Okay. What does exactly 18 look like? Well, how many shots is he taking? 20. How many is he going to make? 18. The probability of making is 0.9, and he wants 18 of those. The probability of missing is 0.1, and I guess I'll have 2 of those. Ooh, I got about a 28.5% chance. Does anybody else get that?
Yeah.
Now, the next one is the doozy. What does at least 18 mean? You can make 18, 19, or 20. Okay, so let's think about this for a second. What am I gonna do, Aiden?
You just do, the same thing for 18, 19, 20, all the products.
Exactly. So this is like 3 problems in one. You have to calculate the probability of making all 20, which we did already. You have to calculate the probability of 19, which we haven't done yet, and then 18. And then when you get all those answers, you're gonna add them up, because it's 20 or 19 or 18. So we're gonna add them up. What's 19 gonna look like? We already have the other 2. What's 19 gonna look like?
0.12.
Yep, that's it. But we're gonna type it all in and add them all up. Now, I already did these separately. Your calculator actually will do this all together, so you don't have any round off there, David.
Is there ever a chance where the second number after the C is not the same as the one that's above the 9?
All right. Are everybody okay with that so far? Because I'm going to throw one more at you. There's a little bit of room there. I'm going to throw in one more. Suppose it said no more than 18. Not that one. What's the probability that he'll make no more than 18, right? Are you thinking right, or what's happening?
Me and Hank are deliberating.
Okay, that's good, keep deliberating, Alana.
Could you just do 17?
Now, no more than 18 would include 17, but what else would it include?
Like, what's 17?
Yeah, it would, well, 0 through 7, actually 0 through 18 is what it would include. Does that make sense to you? Now, let's think about that for a second. We did 3 cases right here, and if we're going 0 to 18, that's gonna be a bunch of cases. Now, they're all gonna be set up exactly like this. It isn't like it's hard, it's just time consuming. So Clayton, what do you think?
Just do it all 100%, minus the percent you calculate there.
Well, it would be 100% minus the 19 and the 20 case. Would you agree with that? So instead of doing 0 to 18, will work. We'll do 100 minus 19 and 20. And that'll give me the rest of it. Does that make sense to everybody? So it'll work either way, but think about it. If you have a situation where you're going to have to do a ton of pieces, think about doing it backwards and doing 100 minus what you don't want. Because sometimes that's faster. Not always, but sometimes that's faster. Okay? All right, 9.3 will be due on Friday. This quarter killing me. I know, we gotta get through this. All right, we have one more topic. I had hoped we'd get to 9.6. We are not. We're going to do 9.6. The juniors might. But the seniors, we're not. There's no way. In the sophomores. All right, 9.4. Alana?
So, if we're writing the answers for that one, then when we just when we put what we said, the one that we get for 100 minus 19 minus 20,
Yep.
or we have to put more than one answer, or just one answer.
Give you one answer. But I do want you to, I've been saving time by not calculating everything out. I do want you on your homework to calculate it out. So type it on your calculator, 20C19 times 9. All right, so 9.4 and 9.5 have to do with sequences and series. Give me a sequence of numbers. Any sequence you can think of. Jake.
2, 4, 6, 8.
All right, that's a nice sequence. 2, 4, 6, 8. Can somebody give me another sequence of numbers? Let's be a little more creative than that. Anybody that can sing and dance like you just said can be more creative than that.
Come on, sing
Let him go, yeah. Go sing.
You should hear him sing. What?
3, 5, 9, 27, 85.
3, 5, 9, 27, 85. All right, how about another sequence of numbers? All right, I'm going to pick another sequence. I'm going to say maybe 4, 16, 64. All right. Now, I'm not sure what's going on here. I have to spend a couple minutes thinking about that. If there's anything going on, I'm not sure.
There it is.
The sequence is in an ordered set of numbers. There doesn't have to be a pattern. There usually is. If there's no pattern, it really isn't worth discussing. So there usually is a pattern, but there doesn't have to be. These two have definite patterns, though, and they are the two main kinds of sequences. We have formulas that help us generate terms and sums for these sequences. Now, tell me about this one. What would be the next term? Okay. And you know that because we are adding 2, they're going up by 2. That is called the common difference. For this sequence right here, the common difference is 2. That is the number that we add to get from term to term. When you generate a sequence by adding the same number over and over and over again, which is what's happening in this one, it is called arithmetic. So an arithmetic sequence is a sequence in which we get from term to term by adding the same number. Okay? Now, this one is not arithmetic. Because how am I getting from term to term here? I'm multiplying by the same number. Okay, I need you to listen and process this. Arithmetic means we're adding the same number. It's not just adding, it's adding the same number. Geometric means we're multiplying by the same number. that same number is called a geometric sequence. And the geometric sequence is one in which we get from term to term by multiplying by the same number. And that same number is called the common ratio. So in this problem, the common ratio is 4.
Does the starting number have to be the common ratio?
No. So you could have 2, 6, 18, that is also geometric with a ratio of 3. Yeah.
Oh, is it also minus in division?
There is no, when we're talking about arithmetic and geometric, there's no subtraction and division. If your terms are going down in your arithmetic, then your common difference is simply negative, adding -2.
So
The
you,
difference is always what you add. Okay, what you add. And likewise, if these terms were going down, it would be multiplying by 1/4 or something, multiplying by the reciprocal. So no, there is no subtraction and no division. You think about it as adding a negative and multiplying by the reciprocal. Okay, David?
Yep.
All right. Now, before we get into the meat of all these formulas and all, got a little background work and some vocabulary to talk about. So number 1 says, look at this formula right here. This is a formula. It is called an explicit formula. And the reason that it's called explicit is because when it says find a sub 5, that means the 5th term. This notation means the 5th term of the sequence. And all you have to do, since it's a sub 5, all you have to do is put 5 into your formula, and the 5th term of the sequence is -17. Explicit means you can find whatever term you want, boom, just like that. So the next one says, find the 100th term. Okay, that's just as easy. It'll be 3 minus 4 times 100. So what is that, -397? That's it. So whatever term you want, you've got this sequence. This is its formula. This one, by the way, happens to be arithmetic. You don't need to know that now, but it is an arithmetic sequence. And somebody gave me the formula. I could find whatever term I want. Now, that is very different than what's happening with the next formula. The next formula is what we call recursive. And here's what it means to be recursive. Let's suppose that I wanted the 100th term of this guy. Okay, I want to find a sub 100. I know that's not what it says, but I want you to see the difference. If I wanted to find a sub 100, then wouldn't I have to let n be 99? So then this formula would say a sub 100 equals 3 a sub 99 minus 1? Well, wait a second. What's a sub 99? The 99th term? Do I know that? No. So I have to find the 99th, but in finding the 99th, I do the 98th. You see? You can't jump ahead. In a recursive situation, you have to build it from the bottom up. So when it says find a sub 2, well, that's easy. Pay attention, there's too much talking. If we have to find a sub 2, then we're going to let n be 1. Would you agree with that? Pay attention to your formula. You want a sub 2. So n be 1. So your formula says 3a sub 1 minus 1. I just plugged in n equal 1. Well, wait, what's a sub 1? 2. So 3 times 2 minus 1 is 5. So the second term is 5. Now it says find a sub 5. So I'm leaving a little room here because I know what's going to happen. A sub 5 is 3a sub 4 minus 1. I can't do that. I don't know a sub 4. So, okay, what's a sub 4? A sub 4 is 3a sub 3 minus 1. I can't do that either. A sub 3. 3a sub 2 minus 1. Oh, that one I can figure out, can't I? What's a sub 2? 5. So this is going to be 15 minus 1, 14. And now that I know the third term, I can find the fourth term. And once I know the fourth term, I can find the fifth term. What is that, 122?
What?
What's your favorite? Do you like explicit formulas or do you like recursive formulas? Explicit, right? Definitely we like explicit formulas better. Some random sequences, and we'll talk about the most famous one of these days soon, can only be generated recursively though. So you have to understand that concept, even though we hope like that we don't have to do it very much. Because it's a pain in the butt. All right, you can't talk about sequences without talking about limits. And limits are extremely important because next year you're all going to be taking differential calculus, and the derivative is a limit. The whole basis of the entire thing is this notion of limits. And so we got to kind of have a sense of what they are. So I'd like you to look at this set of numbers. And I'd like you to tell me where it appears to be heading. So we've got that down, and it's definitely going down. Now, here's what you got to ask yourself though. These things, if you plotted them on the number line, they're like here, right? Now, when you say they're going down, are they going down like this?
No.
What's happening?
Down straight.
Straight down.
It's like there's a line on zero.
Oh, there we go. There we go. There's a wall at 0 because you can see what's happening here. Is it ever going to be negative? No. So the limit of this expression, is 0. Those terms are getting closer and closer and closer to 0. This is not a shock to you. We have already discussed this. If you remember, back when we were graphing rational expressions, and we were going to graph this thing, and I said to you, where is the horizontal asymptote? You looked at this problem and you said, well, this is 4. There's no x's on the top, but there's 1 x on the bottom. So the horizontal asymptote would be at 0. Horizontal asymptotes are limits. I think we talked about that, but frankly I can't remember. Horizontal asymptotes are limits. So if you remember how to find a horizontal asymptote, you got it made in the shape. Look at the next one. Where's the horizontal asymptote for an expression like this? 1. The limit is 1. The limit of the sequence is 1. N plus 1 over n keeps getting smaller, but it never goes smaller than 1. How about C? No limit. C is no limit, we call that divergent.
One of them.
It has no limit. How about D?
It's like a bracket.
Well, Will, you're right, the entire sequence is contained between -1 and 1, right? But as we keep going down the line, you know, -1, 1, -1, 1, as we keep going, if I kept writing that all the way out to Loretto Hall, would I be heading toward a number? No. This one is also divergent. There is no limit. But it diverges very differently than problem C. Somebody said C had a limit of infinity. Well, that's a little crazy to think about it, but it is heading toward infinity. D is just bouncing back and forth between -1 and 1. Neither of them have a limit, okay? No limit for either one. How about E? The limit's 3. Do not be confused. You know how to do this. The limit is 3. How about F? 0. Why is F 0? Because there's no n cubed on the top, right? So some of you may have memorized that if the big power's on the bottom, it's 0. Hopefully you're thinking 0 n cubed over n cubed. You got a question, Blaine? Okay. How about G? That one diverges because you have no n cubed on the bottom, right? Ooh, what about H? I've heard a divergent, I've heard a 1, I've heard a 0, I have heard another none, divergent none, I've heard that.
It's like a slant. 2/3.
I've heard 2/3, okay, we got all kinds of answers, and we actually got the right answer from Mr. Beard himself, right here. He said the limit is 0. Now, kids, I want you to think about what happens when you take the number 2/3 and raise it to higher powers. It goes smaller. 2/3 times 2/3 times 2/3 keeps getting smaller. Would you agree? Now, does it ever go negative? No. So it keeps getting smaller, but it stays positive, which means it's heading to 0. Now, I don't know if you remember this or not, but you knew that too. Because way back in chapter 3, we looked at exponential functions that looked like this. And we said exponential functions are either growth or decay. Remember that? And how did we decide if they were growth or decay? Whether that number right there was more bigger than 1 or less than 1. If that number is less than 1, you are decay. You are heading toward 0. So the limit of this is 0. Now, flip it over and make it 3 halves, and then it becomes a growth problem, and there is no limit. It's all connected, kids. It's all connected. So that's our I. I is no limit. Now, J is a brief introduction to some properties of limits. What is the limit of the first piece of the problem? 4. What is the limit of the second piece of the problem? 1/2. The limit of a sum is the sum of the limits. Oh my gosh, it's so easy. So the answer is 4.5. 4.5. You find the limit of each piece and add them together. In K, you do the same thing, only you don't add them together, you multiply them. So that will be 4 times 1/2. So that one will be 2. Now L.
It's 3 plus 2/3.
What do you think, Jake?
3 plus 2/3.
Jake is exactly right. 3 plus 2/3. The limit of a constant is the constant. So if it's just 3, the limit is 3. And then the limit of the second half is 2/3, so that would be 3 and 2/3. 3 and 2/3. And what about M?
4 minus 5.
4 minus 0. Why is the limit 0?
0
Go in squared on the top. So the limit of number M, letter M, is 4. 4 minus 0. Stop it! Do I have to separate you guys? Or girls? Alright. Anybody have a question about that limit section? We got a general feeling for that then. Okay. So now we're gonna get into the meat and potatoes here of these sequences. What's an arithmetic sequence? Tell me again, what's an arithmetic sequence? You get from term to term by adding the same number. So when I look at letter A, the sequence I'm given is this. And you need to be able to tell that's arithmetic. And you need to be able to tell me that the common difference is 4. That's what I'm adding. Now, I put the formula on the paper, but I want you to kind of understand it. The nth term, or the first term is -6. A sub 1 stands for first term. The second term, we just took -6 and added 4, and that's how we got -2. Then we get the third term, we took that -6 plus 4 and added another 4. So basically, look at what's happening. This is -6 plus no 4s. We didn't add any 4s the first term. This is -6 plus 1 4. And this one's -6 plus 2 4s. So in general, the nth term, this is my explicit formula, the nth term is going to be -6 plus how many 4s? N minus 1. Now in a minute I'll multiply that out. But look, remember the third term was -6 plus 2 4s? So the third term had 2 4s. The second term had 1 4. So the number of 4s is 1 less than your term. Distribute it. So it looks like my formula is 4n minus 10 if I did my arithmetic right. That's your explicit formula. That would be any term you want. Now, the general formula I have written there on the paper, but I want you to see where it came from. In this problem, what was the -6? What was the 4? The difference. So it looks like I take my first term and add my difference times n minus 1. Isn't that what happened here? That's the formula that you will use anytime you're generating terms of an arithmetic sequence. N is the number of terms. So if you want the 100th term, n is 100. This is the first term, and that's the common difference. That'll work for any arithmetic formula. All right? So, for us, what's the 24th term? It says find a sub 24. The 24th term is negative 6 plus 4 times 23. Or if you want to just plug 24 in down here, you can. Is that 86? If you have a need for the 1000th term of this sequence, you can find it. Like that. Now, we want to write a recursive formula in this sequence. So remember, a recursive formula, you find the 18th term by doing something to the 17th term. That's what a recursive formula does. So what do I have to do to the 17th term to get the 18th term of this sequence? Add 4. There it is. There's just one piece missing. You have to know where to start. So you have to add a first term as part of your formula. That tells you where to start. Then you know, okay, I'm just going to keep adding 4 after that. But if all you know is you take a term and add 4, that doesn't do you any good if you don't have a term to start with. Do you see what I'm saying? Does this sequence have the same pattern to it? So how do I know it's that set of numbers instead of this set of numbers? Because I told her to start. Gotta have that. That has to be part of the recursive formula. All right. D looks a little bit crazy. I gotta be careful here. I gotta skip some stuff like that. Yeah. All right. So D. Let's do D, and then we're gonna move on and do some geometric. Find the explicit formula for ln3, ln6, ln12, ln24. Well, first of all, is this thing even arithmetic? This guy right here, okay, so we have ln3. This guy is ln 3 times 2. What do I do when I take the logarithm of a product? You add them. So this is really ln 3 plus ln 2. So how did I get from here to here? I added ln 2. Now let's look at this. This is ln 6 times 2, which is ln 6 plus ln 2. So how did I get from here to here? Didn't I add ln 2? This is arithmetic, believe it or not. Those of you that slept through the logarithm chapter, the what will my formula look like? The nth term is the first term plus the common difference times n minus 1. So when it says find a sub 10, a sub 10 will be ln3 plus ln2 times 9. Right, so far so good. And ln3 plus 9 ln2s. What happens to this 9 out in front? That becomes an exponent. So ln3 plus ln2 to the 9. 2 to the 9 is 512. So this is ln3 plus ln 512. What do I do with the 3 and the 512? Multiplying. So that's ln 1536. That is the 10th term. That problem distinguishes the men from the boys and the women from the girls. Right? Gotta remember a lot of stuff. All right, let's get through geometric and then we'll be done for the day. So here we go. Writing it, geometric. Let's look at this sequence 3, 6, 12, 24. First of all, would you agree that it is geometric? Because we're multiplying by 2. So the first term is 3, and the second term is 3 times 2. And the third term is 3 times 2 times 2, or 3 times 2 squared. Right? That's how I got my third term. I took 3 times 2 times another 2. Do you notice something? What will the nth term be? Now look, the third term was 3 times 2 squared. The second term was 3 times 2 to the first. The first term was 3 times 2 to the 0. There weren't any 2's. So it's 3 times 2 to the n minus 1. So in general, the nth term is the first term times the ratio to the n minus first. So when it says find a sub 10 for this sequence right here, find a sub 10. A sub 10 will be 3 times 2 to the 9. I think that's 1536, but I could be wrong. I'm remembering wrong. That's just coincidence that happened that way.
Since it's like that, could you write the ln one as a geometric sequence as well? Like just say ln of the 3 times 2 to the n minus 1.
Yeah. I guess you could, yeah. It's really not an arithmetic sequence or geometric sequence, but because of the properties of logarithms, it becomes a multiplication. Because you're just putting in another 2 every time, yeah. I want you to think about this for a second. Let's go back in time about 40 years, 38, 39 years, something back in time. And a kid walks into the classroom and says, Mrs. Ford, my dad and I were watching TV last night, and they said something that can't possibly be right. And my dad thought maybe we could figure it out in math class. Well, what is it? Well, they said on TV that if you put 1 checker on the first square of a checkerboard, 2 on the next one, 4 on the next one, 8 on the next one, 16 on the next one, and so on, by the time you get to the last square of the checkerboard, you'll have enough checkers stacked up to reach the nearest star. Now, the sun is the nearest star and is 10 to the 7th miles away. That can't possibly be right. Or is it? Let's think about it. Is that a geometric sequence? Yeah. What's the ratio? 2. So our formula says that the 64th term, get 64 squares on the checkerboard, the 64th term would be 1 times 2 to the 63rd. So if we put in 2 to the 63rd, 2 to the 63rd, we get a huge number. But remember, that number represents how many checkers are there. So let's divide that by about 3. We could argue, but I'm going to say 3 checkers make an inch. So I'm just going to divide by 3. And now I know how many inches I have. Well, it's still pretty big. So let's divide it by 12. Now I know how many feet I have. Divided by 5,280. I have 4.85 times 10 to the 13th miles worth of checkers. That is to the sun squared almost. That's a huge, huge number. Isn't that amazing? Isn't that amazing? So you guys can't imagine, I'm gonna tell you one more story. I don't really have time to look like I'm sorry. You can't imagine me ever being known, but I was. And when I was 22 years old, brand new, fresh off the farm, I went to college at a place that was smaller than Cathedral. I was not ready for the city. This was a city school, I wasn't ready. Because I was brand new, I got what brand new teachers always get, which is whatever nobody else wants to teach. So I was teaching a first-year algebra class.